Chapter 2, we're going to take a look at the concept of derivatives, which is a really big concept in calculus. And this section of material is going to develop what a derivative really is, right? Like what it really means and how it's found in a nuts and bolts kind of sense. And then when we get to 2.2, you're going to be very relieved because it's going to get a whole lot easier to do what we just did in 2.1 the hard way. Okay, so this is the hard way of doing derivatives. And then over time, what happens is that people do things over and over and over again, and they look for shortcuts. Y'all know that, right? You do that in your own lives all the time, right? So 2.2 is the shortcuts for what people could do in 2.1 without them. So we're going to look at the 2.1 stuff, and it's going to sound a little bit familiar because we talked about it on the first and second days of class anyway. We're going to be looking at secant and tangent lines, okay? So this part, if it sounds familiar, should, because we have looked at this before. If you take a look, and we'll start with a general graph. The one I'm going to draw looks like this. Let me make one more mark before I copy it. Let's call this point right here C. So it looks like right here. This is the corresponding value f of c. All right, that'll work. We're going to take a look at secant lines and tangent lines, and I want to draw the same picture on both sides as a comparison for what we're doing. So if you'll remember, a secant line means taking 2 points on the curve and connecting them with a line. So we're going to take another point over here. Let's say it's right here. And we're going to connect those 2 points with a line. This would be called the secant line through whatever this point is that I've got for C. And then this piece right here, which I'm going to call C plus H. It's just some distance away from C. So this piece right here is a distance of H. And up here, or down here actually, because I've drew it to this a little bit lower, is going to be the y value at f of C plus H. So if you look at the bottom part right here, this tells you how we find slope of this particular situation. It's always the change in the y values over the change in the x values. The 2 y values are the ones that are written to the side, f of c plus h and f of c. So they're subtracted in the numerator. And then the 2 x values that correspond are c and c plus h, and they're subtracted in the denominator. And you can consolidate the denominator, right? C plus h minus c would leave you with just h. And the slope of the secant line would be f of c plus h minus f of c over h. Okay, in other words, you find the difference between the y values, you divide it by h because that's the difference between the x values. This is the slope of a secant line. You've been doing slopes since Algebra 1. Tangent lines. All right. For a tangent line, what happens is we take that same value, I probably should have marked it to start with, here, f of c plus h, and we move it closer and closer and closer to the value of c. So our first line that we're going to draw will be the same one we started with from before. That's not good. That's reasonable. And we move our value closer. So we're going to go from there to here. I wanted to change colors. Let's try again. Slightly different color. And the line changes, right? Because the line's now here-ish. And then we move a little bit closer. There we go. And the line becomes this one right here. That's not perfectly linear, but pretend like it is for a second. And they keep getting closer, right? The point keeps getting closer. This value that we're moving away from C is closer to what it was before. So now we'll go with blue. Now we're over here. And now we're through this line. Okay, so the lines get closer and closer and closer together. Eventually what happens is that it gets so close to the point C that we get the slope, we get the tangent line, and it's the slope of the tangent line. So I'm going to erase all these lines. They're on your paper, and I want to draw one single line in now that is the tangent line, or at least an approximation thereof. The tangent line should look something here like this. I realize that the tangent line eventually crosses down here, right? I realize that happens sometimes, but in a nearby area around it, it's just barely touching and bouncing off of the graph, right? It's just touching it, not cutting through it. That's the difference. So this is the tangent line. So what we're going to do is we're going to try to find the slope of this line. But slopes need 2 points. And this only has 1 point on the line if we ignore the fact that it crossed through later, because that's an arbitrary feature that's just of this graph, right? It's not always going to happen. And so what happens is we do a limiting process. And this is why we've worked so hard on limits. If f is defined on an open interval containing c, then, and if the limit as h approaches 0 of f of c plus h minus f of c over h equals m exists, then the line passing through this point with this slope is the tangent line to the graph. This slope of the tangent line to the graph of f at this point is also called the slope of the graph. So we have 2 phrases now that mean the same thing: slope of the tangent line and slope of the graph. And notice the only thing different on this slide than the previous slide is that I have limit at the beginning. The part that's the fraction's the same, f of c plus h minus f of c over h. All that's the same, but now I'm taking the limit as h goes to 0. In essence, I'm letting those points get closer and closer and closer to the point C that I started with, or I'm letting the h value get smaller and smaller and smaller until it's sort of non-existent. Mm-hmm. So when I tell you that in section 2.1, we're going to be doing problems that are not going to be your favorite, the reason primarily is because we're doing limits. And they weren't your favorite to begin with already, were they? Probably not. So we're going to be taking a look at limits again from this very specific perspective of the h value going to 0 every time. Okay? We're letting points get very, very, very close to a specific point that we're given, or a generalized point that maybe we're not given, just x in general, and we're going to find the slope of a line. So this is the first one we're not going to do. Notice they do give you an actual point here, 1, 5. We're going to see on problem, I think it's just the next problem actually, where there's not a point given. This one wants us to find the slope of the tangent line to the graph at the given point. Because it gives us a point, our answer, when we're all said and done here, is going to be a numerical value. Like we're going to have something like 5 or 2/3 or something. We're going to have a number at the end of this because we're actually given a point. So what I'm going to do with you is what is called the 4-step method. This is not the only way to do this problem, so I'm just going to warn you right now. So if you go to the Success Center, they should be familiar with what I'm doing, and that's fine. But there is another way to do this. I think it's a little bit more confusing, so this is the way I'm going to show it to you. If you don't like this method, or if you've had some calculus in the past and you know how to do it the other way and you like that better, feel free to do that. There's nothing wrong with you doing it in a different way. Or if somebody else shows you this different way and you're like, nope, that one really resonates with me more, then go with it. But I'm going to show you from one direction. I'm going to show you what's called the four-step method. Okay, so this is the four-step method, and what the four-step method does is it breaks apart that limit definition, which I'll write here at the top, into four pieces. So this tells us, actually I'll call it M for now. M equals the limit as h approaches 0 of f of x plus h minus f of x over h. Notice I've just replaced the c with x's as a generalized approach here. You could use c if you want to, but I'm going to be doing some algebra. Kind of like doing algebra with x's myself. So step one. Step one is to do f of x plus h. Okay, so step one is this piece of the definition in red. Let me erase the red I did before. So this is step one in red. What does f of x plus h mean? Well, what would it mean if you did f of 1? What would that mean?
Plug 1 into the equation.
You bet. Plug 1 in for x, right? We'd go 6 minus 1 squared. That's what it would mean if I had a 1. I don't have a 1. I have an x plus h, but it means the same thing. It means I plug in, or I substitute in, x plus h in the place of x. And I simplify with algebra. Now, you need to be careful. X plus h squared is not x squared plus h squared. Okay? I get that all the time. I got it recently in my Calc 2 class. It happens. We forget. We just want to distribute stuff. It doesn't work like that. X plus h squared means x plus h times x plus h. So I'm going to belabor the point right now and actually write it out. I won't do this again. But that's what it means. And we're going to distribute that out. So we're going to FOIL. First is x squared. The outer and the inner are both x plus h. I'm sorry, x times h. So we have two of those, two xh's. And then my last term is h squared. And then I'm going to distribute the negative through. So step one, typically, it depends on the function, but typically it's the step that's kind of messy in terms of cleaning it all, like cleaning out all the parentheses. Step two and after are steps where it consolidates and it reduces things and cleans them up, typically. I think I have an example where that's not true as well to show you, but step two is to take what I just did as f of x plus h and subtract f of x. So you'll notice that's the entire numerator above. So this piece right here is everything up here now, the entire numerator that I'm working with. Okay, so I'm taking this expression that's in the in the top of my screen, and I'm just going from sort of like the inside out, right? Kind of like order of operations. I'm working from a small piece, and I'm going to extend it to get into the entire fraction, and eventually the limit will be my last step. So I take what I just did, 6 minus x squared minus 2xh minus h squared, and I subtract f of x. I know I'm using f's, and this is g on my function, so let me just change it so that I'm not mixing notation. We'll call this f now. So I subtract off what I was originally given for my function, which is 6 minus x squared. And as promised, I do in fact see things start to cancel. What do you see that will cancel? The 6's. Yep. This right here is now a minus 6 because there's a negative on the outside right here, right? So the 6's are going to cancel. What else is going to cancel?
X squared.
The x squared is going to cancel. This one's negative x squared, and then when I distribute the negative through there, I'd have positive x squared. So in particular, everything in the original function, right, that parentheses that I just put in, will not remain. It will reduce with something I already have. Okay? Almost always going to happen like that. So what happens is I end up with a smaller expression than I had before. Now I have negative 2xh and minus h squared. Less is more. We really appreciate it, right? We appreciate that there's less going on now. So looking back at my original definition at the top of my screen, what do you think step 3 might be? Dividing by h. That's exactly right. So step 3 is going to take, and I'll write it out, it's the f of x plus h minus f of x on the previous step, and I'm dividing it by h. And in particular, what that is that this is the entire expression up here without the limit. Now, in terms of what I'm actually working with, this means I take negative 2xh minus h squared, put it over h, and if I've done it correctly, I will be able to cancel that h that I just put in there out with the pieces in the numerator. If I can't, I've made a mistake and I need to go back and figure out what it is. So if at this point, there's not an h in every piece up here, I've made a mistake. Is that okay? There is. So I will be able to reduce the h on this. So this h and one of these h's cancels with the h in the denominator. Remember, from a fractional standpoint, you can only cancel them if they occur in every single piece of the numerator. You can't just do this. This does not work. My 9th graders are learning this very well right now in algebra. They keep trying to do this. Can't do that. It's got to cancel with all the pieces. So that will leave us with, if we reduce on this one, negative 2x and minus h. Is that okay? All right, I'm out of space, so I'm going to, do I have another slide? No, I don't. Okay, I'm going to consolidate this a little bit, make it smaller. There we go. And we'll do step 4. Step 4 is the conclusion. It is the last piece, and it's taking the limit as h goes to 0 of the expression entirely. So it's the entire thing put together at the very end. Which means it's the limit, you're going to write it down, as h goes to 0 of what you got on the previous line. I'm sorry, didn't mean to write that long. Negative 2x minus h. Okay? So this whole piece right here is the piece here, and it's showing up here. And we're just putting the limit on the front. That's all that's happening. But just like you did in all the stuff in chapter 1, if it says h is going to 0, we actually put 0 in now for h, and we can. Notice we couldn't have done it on any previous step, right? Because there's still dividing by h going on, and I can't divide by 0. Right? The goal at the end is the same. I want to plug in 0 for h. But until I get through steps 1 through 3, the h still resides in the denominator. Yeah? And I can't do it. But once we get to step 4, we can. So if I put 0 in for h, I have negative 2x minus 0. And what will this equal? Just negative 2x, right? Now that doesn't quite answer the question, but we are done with the limiting process. This is the limit process that we needed to go through. The last thing we need to do is to go back and remember that we were given some information about a point, and we haven't done anything with it, this 0.15, right? So what happens last, so the last step here, and it doesn't happen on every problem, but it happens because I was given the point. The last step is to take the point, 1,5, and to take our expression that we just got, my m equals negative 2x, and it's to put the x in that I was given. I was told x is 1, so I put in the number 1, and negative 2 times 1 would be negative 2. So if I was not given a point, 1,5, I wouldn't even do that last step. I would have been done when I got to negative 2x. Now the nice thing about doing this in this order, too, is that let's say that you were given the 0.15 and you're supposed to find the slope there. Well, you can do that. You can just put in the number 1. But then you're also asked to use the same function and find the slope when you get to x equals, or I don't know about the 0.06. Okay, well that means at the last point I plug in x equals 0. Or maybe I was asked to plug in x equals 7. I put in x equals 7. Okay, the number itself, 107, whatever I'm using for x, doesn't muddy the waters. It's just used at the very end as an evaluation step when it's asked for it all. Okay? Now what we are actually finding, which was called the slope of the tangent line and the slope of the point, or slope of the curve, both of those are valid descriptions, but it has one more name that we're going to be using more frequently, and that name is the derivative. So what we just found, this slope that we just found, is actually something called a derivative. So the derivative of f at x is f prime of x, right? That's the slope. This is the same m that I just did before. It's equal to limit as h goes to 0 of f of x plus h minus f of x over h, provided the limit exists. For all x for which this limit exists, f prime is a function of x. So this is telling you if you start out with a function and you do this process, you get another function.
Should we write m or the f?
F prime of x. I'm just reminding you that that's what it was from the previous slide. On exam 1, you guys blew me away, and everybody, percentage-wise anyway, most of you memorized what I asked you to memorize. This is the one we're going to memorize for chapter 2. Mark it now. But be grateful, because it's not that one, right? Okay, so now we're all like, okay, that's not so bad. It's half as long. It's got a lot of the same information in it, but it's half as long to memorize. This is the one we're going to memorize here. At some point. So we need to do some more examples because this limit process gets easier the more we practice with it. That's how most things in math are, right? The first time you do them, you're a little bit uncomfortable, and about by the 4th, 5th, 6th time, you're like getting the hang of this, starting to see the pattern, making sense. So we're going to do some more examples with some different types of functions. This is our next one. Our next one is not a polynomial. The first one was a quadratic. It was a polynomial. This one's a rational function. So there are going to be pieces of this that are going to feel a little bit different because of that. But the 4 steps are the same. They just play out a little differently. So I'll remind us our definition, and now I'll use the notation that's f prime. This is the limit as h goes to 0 of f of x plus h minus f of x over h. There we go. And we're going to do the same 4 steps we did before. If you're going to do the steps like I'm doing it, at the very least, number them 1, 2, 3, 4. You don't necessarily have to write all the descriptions that I'm doing every single time, but number them so I know when your steps have changed from step 1 into step 2. Because it's not true, let me go back over here, that, for example, this piece is equal to this piece. Right? They're not equal to each other. Right? This is a new step with a new description at the front of it. So at the very least, number your steps so that it's clear that you understand these are not equalities that we're doing. So in our 4-step method, I'll continue to label mine out. We're going to do f of x plus h. So what will f of x plus h look like for this function? Can you take a step back, David, for just a second? What would it look like before you start distributing?
That would be 1 over x plus h squared.
Good. So let's start with that. Okay. That's what it would look like. And then David was already starting to distribute for us. So again, this is not x squared plus h squared. We have to FOIL this out. I've already done it once, so I'm not going to write it all out to do it again. But it's x squared plus 2xh plus h squared. And if you don't want to think about it, you can memorize that too. It's always going to be that way. So that's another option here. Okay, so as promised before, it's the messy step right now, right? That looks pretty messy. There's nothing I can do to consolidate or clean it up. I just have flushed out all of the parentheses by distributing, right? That's the goal in step 1. Step 2 is to take the f of x plus h and subtract f of x. So on this step, I have this expression I got before, and I'm going to subtract the original function I was given.
That's gonna be even more messy.
This one becomes even more messy. This is the exception to the rule that I mentioned, the process that I mentioned last time. This will be messier. What do you have to do in order to subtract fractions?
Have to have the same denominator.
Yeah, we need the same denominator, right? And you can't just go tacking on the 2xh plus h squared. Like, in order to have the same denominator, they have to have factors that are the same, which means that these two denominators are in no way, shape, or form like denominators, so they'll simply have to be multiplied by one another. So I'll change colors to designate that that's what I'm doing. We're going to multiply the first one by x squared. And whatever you do the denominator, you have to do the numerator. And we're going to multiply the second one by x squared plus 2xh plus h squared.
Ew.
Ew, I know. Our numerators are going to simplify after we've done the multiplication, but the denominator is going to stay ugly for a little while. Now, you don't need to distribute the denominator. That is not going to be helpful. Leaving things in factored form is a perfectly reasonable way to leave things for calculus in, I think, every situation. I can't think of any situation where the answer written all the way out is what we're going to be wanting, okay? If it's completely factored. If I change that later, don't hold it against me. Okay, x squared plus 2xh plus h squared is the denominator times x squared. That's the denominator for both of these. The first numerator is just x squared. The second numerator is going to be this piece over here with the negative that's in front, so I'm going to distribute that negative as I write it out. So this is negative x squared minus 2xh minus h squared. And there is something that reduces at this point, right?
X.
Yeah, the x squareds. So you may not feel like you've made a whole lot of progress, but there is a bit of progress, a bit of cancellation that happened to yield where we are now. All right. Y'all ready for step 3? Okay. Step 3, we are going to see something simplify. So step 3 is to take the same thing we just did, f of x plus h minus f of x, and to divide it by h. So dividing by h is the same thing. I'm going to write it out to prove it, well, to remind you, not to prove it to you, but to remind you. All of this over h looks terrible. But dividing by h is the same thing as multiplying by the reciprocal of h. What is the reciprocal of h? Yeah, 1 over h. So you could definitely have jumped straight to that. I'm not going to even write it as dividing by h. I'm just going to write it as multiplying by 1 over h. And then looking at things from a fraction standpoint, I can look at cancellation between this numerator and this denominator, and I will have some success in doing so. The h, like notice right now, if I tried to plug in 0 for h, I would still have a problem because h is still in the denominator, right? Eventually, that's my goal, put 0 in for h, and I can't do it here. That h that I just introduced in the denominator, the reciprocal piece, has to cancel, right? That's what has to happen in step 3. So we notice the 2 parts that I circled in blue, it will, in exactly the same way that it did over here, right? There's an h in each of the pieces, 2xh and h squared over h. Same thing happens here. I have a 2xh and an h squared and an over h. The signs are maybe a little bit different between them. Actually, these two might be the same. And so we do, in fact, have them canceling. So I have this h cancels with one of these and this one. That leaves me in the numerator with what? Negative 2x and minus h, right? Denominator is the same. It's ugly. We're just going to keep rewriting it until we can deal with it. Like that. I'm going to make my typing smaller one more time. Not typing, but writing. Step 4. The limit is, keep writing x, h goes to 0, of f of x plus h. Again, you don't have to write this out, but if you write number 4 for me, I'll be okay with that. F of x plus h minus f of x over h. That's what I'm actually doing. Okay, notice it does not say limit equals. It is the limit of something. It's like you would never say x square root equals. Square root doesn't equal anything. Square root of something equals it. It's the limit of something. The limit of the previous step, which was negative 2x minus h over x squared plus 2xh plus h squared times x squared. All right. Can I put in 0 for h now? I can. H is no longer a factor in the denominator, causing the entire denominator to be 0. I can put 0 in for h now. I'm going to get negative 2x minus 0. Feel free to not show the zeros if you want. X squared plus 2x times 0 minus 0 squared times x squared. And if we clean this up, I have negative 2x on top. This one's 0, this one's 0. What do I get on bottom?
X squared plus 2x. No, x squared. X to the 4th.
X to the 4th, yeah. I have x squared on the inside of the parenthesis and x squared on the outside. That's x to the 4th. I need to do one more thing, though. What do I need to do at this point? Yeah, what will I be able to simplify, Kingston?
Next.
Yeah, there's an x on the top and an x on the bottom. So this is terrible board writing. Should never do this, but I'm doing it anyway. We're going to cancel an x out. That's going to give me negative 2 over x cubed. And in this problem, I'm finished. On the last problem where it said last step, I had been given the number 1, 5, right? So I had one more step where I had to put the number 1 in. I don't have an ordered pair on this one, so really get to stop at negative 2 over x cubed. All right, so we're going to pause there for today. What I will do is I will be posting a video. The video that I post will tell you, if you're not starting at the beginning of it, where you're starting. It may be starting at the beginning, but I don't remember. But it's going to be posted from what I did last semester, okay? And it will include the rest of this section. So it'll include examples 3, and then that back page where it talks about or where derivatives don't exist, and about differentiability and continuity, okay? So it'll include the rest of that in a separate video. That's what you have to consider your video, if you will, for Monday. If you want to wait till Monday to watch it, feel free. It's fine. And then on Wednesday, you'll have an additional video for 2.2. But all of these will be posted inside of Canvas this afternoon. So if you wanted to do it ahead of time and have a little bit less of a working schedule for next week, you could do that. Just pay attention to the WebAssign due dates.